Welcome to AP Biology. Today we're going to talk about the effects of natural selection. They can be directional, diversifying, or stabilizing. So AP might give you a graph like this, and here is the frequency of individuals of this phenotype. In this case, the phenotype is the color of the fur. So this graph is showing you that most of the mice or moles or whatever they are a medium color, but a few of them are darker and a few of them are lighter in color. It could be any phenotype along here. It doesn't have to be color. It could be weight or height or size of beak or resistance to an antibiotic. It could be anything. So if you can imagine a hawk or an owl or something eating up the light colored ones, maybe the dark colored ones blend in a little bit more, you would see the population shifted this way. Be careful with this graph because they're changing the original population from a solid line to a dotted line in this case. So always pay attention to how they label the graph. So that one is directional selection. So directional selection shifts the frequency curve for some phenotype, right, for the way you look, some phenotypic trait or character in one direction by favoring what had been rare. So the darker colored ones had been rare before, and now they're more common. It might not look like a bell. It might get shifted to look something more like this. Whoops, that's not an awesome picture, but might get shifted to look, I don't know, like that. Ooh, bad picture still. Anyway, might not be an exact bell. Okay, diversifying or disruptive selection happens when some middle phenotype is selected against. So in this case, we've got dark rabbits here and medium ones and light ones like that. So this is not time along the axis. This is just some phenotype, in this case color. And so perhaps the dark bunnies blend in and the light bunnies blend in, but the gray bunnies don't blend in, and so they get eaten. So this is favoring each extreme and not favoring or selecting against the middle phenotype. This might possibly be the beginning of a sympatric speciation event, or maybe it's not. Okay, stabilizing selection finally favors the intermediate, the middle guy, the guy who is already more common but now is getting even more common, and decreasing the frequency of the ones on the extreme. So an example of that, besides phenotype, besides color, an example would be birth weight. So babies who are really little or really big are less likely to survive, at least before we had cesarean sections and great ICUs. All right, balanced polymorphism. So this is a word I want you to be able to sort of dissect. So morphology is your shape. Poly means many, so it sort of means many shapes. But if we're talking about, a lot of times we use this term to talk about DNA. And so let's say the DNA for the hemoglobin, for the normal hemoglobin gene is ACCTGA. I actually don't know what it is. I didn't look it up. Maybe there's just one mutation. Instead of ACC, it goes ACA, and then TGA, et cetera, et cetera. So here's the difference. So there are these two different alleles. That's a polymorphism. That's all it is. There's more, not really shape, right, but the structure of your DNA. And so there's more than one, that's all. So balanced polymorphism is just saying that two different versions of a gene are maintained in a population because individuals carrying both versions are better able to survive than either alone. And so in this case, if you have two alleles for the normal hemoglobin, you do great unless the malaria parasite gets into you and gets into your red blood cells and then kills you. Malaria is a pretty horrible disease with a pretty high mortality rate. If you have sickle cell anemia, you have two alleles for the sickle cell trait. If that happens, it's just a really tough disease. Your hemoglobin tends to become fibrous instead of globular, and it tends to make your cells sickle like this, and they don't go through capillaries as easily, so they get stuck in your littlest blood vessels, and then the blood can't keep going, and so cells die, and so really, really bad disease if you don't have treatment for it. But if you're heterozygous, you have enough of the normal hemoglobin that your red blood cells are typically okay. But if the malaria parasite gets into you, it gets into your red blood cells, and it will take out enough oxygen that with half of your hemoglobin being the sickle type, it'll take enough oxygen out that your red blood cells will actually sickle. And then your white blood cells come over and say, yum, yum, eat them up, and you live another day. So this protects you from malaria. So there's actually an advantage here. So we see way more sickle cell anemia than you would think, given the severity of this disease, because there's an advantage for the heterozygous folks.